In this video, we're going to be looking at section 2.2, is the addition property of equality. A linear equation in one variable x is an equation that can be written in the form of ax plus b equals c, where a, b, and c are real numbers, and a cannot equal 0. Some examples of linear equations in one variable is 3x plus 7 equals 9, where a would be equal to 3, b would equal to 7, and c would be equal to 9. If we have negative 15x plus 45, it's still a linear equation. A is equal to negative 15. The b value would be 0, which we know we don't write. That's why there's no constant on the left-hand side. And the c value is 45. And then for x equals 6.8, it is a linear equation with a being that invisible 1. We know that x represents 1x. The b value is 0, and then the c value is 6.8. Some examples of nonlinear equations would be 3x squared plus 7 equals 9. X squared is not linear. Negative 15 over x equals 45. When we have x in the denominator of a fraction, it's not a linear equation. And then the absolute value of x equals 6.8. That's not linear either because of the absolute value symbol. Nonlinear means if you tried to graph those solutions, your graph would not be a straight line. The adjective linear contains the word line, as I just mentioned, and as we shall see later, linear equations are related to graphs whose points lie along a straight line. When solving linear equations, our solution is an equation with a variable isolated on one side and a number on the other, like x equals 6 or negative 4 equals y. An example of an equation is given as 5 plus 8 equals 13. The right and the left sides must have the same value. So any change made to one side must be made identically to the other side to maintain the equality. So 5 plus 8 equals 13. If we add 3 to the left-hand side and have 5 plus 8 plus 3, we need to add 3 to the right-hand side as well, 13 plus 3, in order to keep the same values. If we replace the 5 with an x in the above equation, we can similarly take and solve for x by subtracting 8 from both sides. So if x plus 8 equals 13, and we subtract 8 from both sides, we would get x equals 5, which of course we knew from the beginning. Whenever a quantity is added or subtracted from one side, we must add or subtract the same from the other side. This is called the addition property of equality. Addition property equality, if a equals b, then a plus c is equal to b plus c. So in solving, we try to isolate the variable by getting all the variables on one side and the numbers on the other. This may involve using the addition property twice, once for the variables and once for the numbers. So let's take a look at some more examples. We have x plus 9 equals 13. And we want to know what the value of x is. I think we know that 4 plus 9 is 13, but let's solve it using our properties. And so if we think of our equal sign as a balance, we have the left side and the right side. Remember, what we do to one side, we do to the other. We see adding 9 being done to x, so we need to undo it. The opposite would be subtract 9. Put underneath instead of next to it, which means on the other side of the equal sign, I have to subtract 9 as well. And then let's simplify. We will bring down our x. We didn't do anything to change that. 9 minus 9 is nothing, so I like to put a 0 around those to show that I canceled them out. And then 13 minus 9 is 4. Oh, excuse me. For b, x minus 8 equals negative 6. Again, here's our equal sign. So what we do to the left-hand side, we need to do to the right. And we see 8 is being subtracted from x. And so the opposite would be adding. So let's add 8 to that side so we can zero out those 8s. But that means we have to add 8 as well to the other side of the equal sign. And so bring down our x. Negative 8 plus 8 is 0. And negative 6 plus 8 is 2. So it's 2 minus 8 to get negative 6, where x equals 2. For C, we have the x on the right-hand side, but that's okay. We're still going to do the same thing. Here's where our equal sign is. We have 5 equals x plus 12. So the side with the x, what we see that we need to get rid of to solve for x is the plus 12. And so we'll subtract 12, which means across from the equal sign, we have to subtract 12 as well. And 5 minus 12 is negative 7. And then we'll bring down our x, and 12 minus 12 is 0. And so our answer is negative 7 equals x. D involves fractions. So that means we're going to have to get a common denominator. Here's my equal sign. 1/4 is being added to x, so we'll subtract 1/4. We'll subtract 1/4 here. And so let's get our common denominator. The common denominator for 4 and 5 is 20. 5 times 4 is 20, so 3 times 4 is 12. And 4 times 5 is 20, so 1 times 5 is 5. And remember, we're subtracting, so 12 minus 5 is 7 over the common denominator of 20 on that side. On the left-hand side, our 1/4 minus 1/4 zeros out, and we'll bring down our x. So x is equal to 7/20. Let's take a look at some more examples. For E, we have 4x equals 3x plus 7. So notice we have x's on both sides of the equation. So we're not just going to be moving constants this time, we're going to be moving our variables. So notice the only thing that's on the left-hand side is x. On the right-hand side, we have an x, and we have our constant. So that means all our x's have to be to one side. In this case, it involves moving our 3x. We don't want to move our 4x over because then there's nothing left on the left-hand side. So moving a 3x makes more sense. It is added, or it's a positive, and so we'll subtract it. And so 4 minus 3 is 1. Remember, 1 is not needed, so we can just write x. And then on the right-hand side, 3x minus 3x becomes nothing, and we see 7. So x equals 7 here. F is the same thing, where we have x's on both sides of the equation. So let's go ahead and take the negative 2x and get rid of it. So all of our x's are on the right-hand side. We see minus 2x for negative 2x. So we change it, make it a positive or plus. And negative 2x plus 2x zeroes out. And we'll bring down our 1. And we have negative x plus 2x. Remember, negative x is the same as negative 1x. So we have negative 1 plus 2, which is a positive 1x. Again, the 1 doesn't need to be written, so 1 equals x here. For G, notice we have a constant and a variable on both sides. So let's take a look at that. Again, here's my equal sign, so when I do to one side, I have to do the other. First, let's look at our x's. We need our x's to go one way. And the best thing to do with the x's is to move the smallest amount to the larger amounts, because that potentially avoids having negative numbers in your exponents. And let me show you what happens if you do that. Let's say that I want to move my x's to have them both on the right-hand side. And so when I have negative 5, x being subtracted to get rid of it, I have negative 5x over here as well. And so when I simplify, my 5x is 0 out on the left, and I'll bring down my negative 1. Don't forget that sign there. And then 4 minus 5 is negative 1. Since this lesson is really only dealing with the adding and subtracting, and we'll deal with those coefficients of x later, that's not what we need to do, but let me show you what happens when we do that. Just in case you have an example like that, you know what to do. But we'll talk about it more in the next lesson. So now all the x's went right, so our constants need to go left. So then minus 8 needs to go. And so we'll do the opposite, or add 8 to both sides. Negative 1 plus 8 is 7. And 7 equals negative 1x. The 1 can disappear, but the negative sign can't. So that's why I always leave it there. And then we have a multiplication. It's negative 1 times x. Just like doing the opposite for adding and subtracting, we get rid of multiplication with division. So we would divide the negative 1 off of both sides, which just changes the signs of both. Negative 1 divided by negative 1 is a positive 1. So we get a positive x on that side. And 7 divided by negative 1 is negative 7. So if you end up with that negative in front of your x, then both sides end up changing signs. We need that to become a positive, so whatever sign your sign is on your constant, it'll end up switching when you think of dividing off that negative 1. But if you were to think of moving the smaller to the larger, it would avoid that last step in this case. So let's look at it that way. So let's move the negative 4x this time. So we're moving all of our x's to the left. And notice I lined it up to where the x's are above each other, so I don't get confused by trying to combine like terms that aren't really like terms. 5 minus 4 is 1, so we have a single x here. We'll drop down our minus 1, and then I'll drop down our negative 8. Again, be very careful that you're not losing that subtraction sign into your problem. And then our last step is to get rid of the minus 1 to get x by itself, so we have to add 1 to both sides. And notice we get the same answer, x on the left when we cancel out our we zero out our 1's, and negative 8 plus 1 is negative 7. So either way, we get negative 7 as an answer. And then for h, we have x minus 1/9 is equal to negative 2. So let's take a look at that. We have x only on the left-hand side, so we have to get rid of that constant of minus 1/9. So we'll add 1/9, which means we have to add 1/9 to our negative 2 as well. And so we'll zero out our minus 1/9 and plus 1/9 and leave us with x on this side. And let's turn negative 2 into an improper fraction by putting it over 1. And then we'll get an LCD, which we can use as 9s. So our 1/9 will stay. But to turn 1 into 9, we're going to multiply by 9. So negative 2 times 9 is negative 18. So negative 18 plus 1 would be negative 17. So our answer is negative 17/9, or negative 1 8/9 if you want to turn it into a mixed number. Let's look at another one dealing with fractions. We have negative 1/2 equals x minus 2/3. So again, here's our equal sign. On the side with the x, we see minus 2/3, so we'll add 2/3, which means we have to do negative 1/2 plus 2/3. And I'll put my work over to the side to show my common denominator. So we have negative 1/2. Between 2 and 3, we can only use 6. And then plus 2/3. That equals something over 6. So there's my structure. 2 times 3 is 6, so negative 1 times 3 is negative 3. And then 3 times 2 is 6, so 2 times 2 is 4. And when we add negative 3 plus 4, we get positive 1, so we get 1/6 left. So it's 1/6 that x is equal to in order to have a true statement there. So notice that each side must be simplified before solving, so the like terms must be combined. If this is not the case, then that must precede using the addition property. Notice you may need to distribute before you can even combine like terms. So we're given a couple examples where we have to simplify before we can solve for x. So this is where some people get confused with. So when I'm dealing with my sides, I'm treating it just like an expression that I'm simplifying. So when it comes to combining like terms, we're not doing the opposites. Many people want to do this, plus 4x here, and then plus 4x here to zero out this. But notice what I did. Here's my balance, and I added 4x twice on the left. So that's adding 8x to one side and adding nothing to the other. So we cannot do that. We have to think of simplifying by combining like terms, and it might help to rewrite them next to each other. So we have 5x minus 4x plus 7 equals negative 2. So now we can see that we're not going to add 4x to both of those pieces. We're doing 5 minus 4 to get 1. 1x, we'll drop the 1 and leave just the x. So x plus 7 equals negative 2. Now we've simplified, and now we can start thinking of doing the opposite. We see minus 7 or plus 7, so we need to minus 7 or subtract 7. So again, now I'm able to go from the left side of the equal sign and the right side of the equal sign and do the same thing to keep things balanced. So x in this case would equal negative 9. So same thing. Here's my equal sign. So when I'm dealing with just over here, I'm combining like terms. So we'll do negative 3 minus 1 more to get negative 4. Negative 4 plus 5 is positive 1. So all those combined together gives us x. And then we'll bring down our plus 7. There's no other constants to add to it. And then on the right-hand side, we're just combine our 8 and our 13 to get equals 21. And so now that I've simplified, now I can do the opposites. So we're going to subtract 7 to get x by itself. So we need to go across the equal sign and subtract 7 as well. And so x is by itself now when we zero out our 7s. And 21 minus 7 is 14. Let's look at a couple more. For L, we have a distribution that we need to do. So again, let's simplify this left-hand side. 4 times x is 4x. And don't forget to do 4 times 1 is 4. So subtracting 4 is equal to 3x. Here's one where I think it was just poor planning on their part, because again, we're going to get a negative that I mentioned we're really not supposed to have to deal with in this lesson. But I already taught you how to do that. So let's take our 4x and move it to the right-hand side, only because there's only x's over here. It doesn't make sense to have to move the 3x to the left and the constant of 4 to the right. It's just adding steps that make it confusing in my book. So since only x's are on the right, we'll move the x's that are on the left to the right, and we'll get rid of the 4x by subtracting 4x. So let's bring down our negative 4. Again, don't forget that sign with the 4. And then 3 minus 4 on the right is negative 1. And so then our last step is to get rid of that negative sign by subtracting off the negative 1. And so we'll subtract off that negative sign with the 4 as well. So we'll get positive 4 equals x. And notice I'm not zeroing out the negative ones because we're not adding them. We're dividing, and technically anything divided by itself is 1. So we're creating that invisible coefficient of 1 when we divide. And then for M, we have a lot of stuff going on. So let's look at just the left-hand side for now and simplify. First, distributing the 2 into our first parentheses. So that gives us 2x plus 2. And now we'll distribute our 3 into our second set of parentheses. So that gives us a 3x, so plus 3x, and then minus 6. And then on the right, there's nothing to do except for just bring it down. So 4x plus 17. So on the left, let's start combining like terms. So we have a 2x here and a 3x here. So that gives us 5x. And then the 2 subtract 6. That will leave us negative 4. And that equals 4x plus 17. Now that we've simplified both sides, we can start moving things. Let's move our 4x to our 5x. Again, move the smaller amount to the larger amount. So 4 is positive, so we have to make it negative or subtract it from both sides. So those zero out there, and we're left with negative 4 on the left. And, sorry, x minus 4, I forgot to do that. 5 minus 4 is 1, so 1x minus 4 is equal to 17. And now our final step to get x by itself is to get rid of the negative 4. So we'll add 4 to both sides. So we'll bring down our x. Minus 4 plus 4 zeros out. And 17 plus 4 is 21. Let's look at an example using a story problem. There is a relationship between the number of words in a child's vocabulary, V, and the child's age, A, in months. For ages between 15 and 50 months, inclusive means includes the 15 and the 50. This relationship can be modeled by the formula V plus 900 equals 60A. Use the formula to find the number of words in a child's vocabulary at age 30 months. So age of 30 goes in where our A is. So V plus 900 equals 60 times A, or we're replacing 60 with 30. So now, again, here's our equal sign. Let's just go ahead and simplify the right-hand side first. So we'll leave our V plus 900 alone. And then 6 times 3 is 18. Add 1 0 from the 60 and 1 0 from the 30. So 60 times 30 is 1,800. And so now just to get V by itself, we have a subtraction of 900. And so our V is equal to 900. And again, this is a story problem. And so that 900 represents the amount of words the child can speak. Okay. It is time for you to practice pages 57 and 58. Nope, just 57. You have one page of examples to do. If you have any problems with any of them, don't hesitate to shout out to me and I'll be more than happy to help you out. Otherwise, I'll see you next time.